Hello and welcome to the module Microcontroller Basics. In this module we're going to be taking a look at how we use the Arduino microcontroller to control both of our motor drivers to enable us to get the robot to do exactly what we want. The Arduino microcontroller that we're using takes 10 volts on the input. The Arduino has a 5 volt linear regulator built in which will generate a 5 volt rail, and so we don't need a separate 5 volt power supply in order to power all of our sensing and control circuitry over here. Make sure that you've tested for shorts on your 5 volt rails before you try and supply them with the Arduino, because you can overload the linear regulator and break it and you'll have to buy a new Arduino. Additionally, make sure that all inputs and outputs from your Arduino are only 0 to 5 volts. Voltages between those are alright, but do not supply any of the pins on your Arduino except for the 10 volt input with 10 volts. This is another easy way to break your Arduino and requiring you to buy another one. If we take a little bit closer look at the Arduino board, we can see we have a number of inputs and outputs on these black rails top and bottom. The brains of this Arduino is an Atmega 328P microcontroller. You can see here it's the large chip. This is an 8-bit RISC microcontroller. Now this is really what gives the smarts to the Arduino. There's nothing special about an Arduino board. It's just a small microcontroller board with all the peripherals necessary to run this Atmega 328P. Now we can take a look at what some of these other components are. We have a crystal clock generator up here, and that's this little shiny oval that generates the clock for our Arduino. We also have another clock generator down here, which is much smaller. We have a reset button you can see here, and some decoupling capacitors for our power supply. These are just like the decoupling capacitors that you use. Additionally, we have an op-amp, which is going to select which power input we take, because we do have a barrel jack connector, which we could input 10 volts on, or we can input 10 volts on this V-in connector here. And this op-amp will determine which one power actually comes from. Here's our 5 volt linear regulator, which generates the 5 volts we'll use for the rest of our control circuitry. We've also got a second Atmega chip right here, which deals with communication to a computer. This allows us to program the Arduino fairly simply using just a USB port. Now the Arduino has a number of different inputs and outputs, so we're going to run through the different types and what their capabilities are. The simplest type of input and output are digital inputs and outputs. These are all on this upper rail here. There are 14 different pins that we can use for these digital inputs and outputs, labeled 0 through 13. Now digital inputs are values between 0 and 5 volts, and ideally only values of either 0 or 5 volts. When we read a digital input from our Arduino, the Arduino is going to read either a 1 or a 0. And that's going to 1 corresponds to a high level input, 0 corresponds to a low level input. Now there is a little bit of wiggle room around each of these rails, so if you supply this with half a volt, you'll probably still read 0, and if you supply it with 4.5, you'll probably still read 1. But it gets a little bit iffy if you're around 3 volts or 2.5 volts. It's really unclear what the Arduino is going to read for that voltage level. So make sure that if you're using a digital input, the value you're trying to read is as close as possible to either 0 or 5 volts. Additionally, we can have digital outputs, which just goes the other way. We'll either tell the Arduino to write a 1 or to write a 0 to that output. And if we've said write a 1, it will generate 5 volts on that output. And if we said write a 0, it'll generate 0 volts on that output. We can also use some of these pins as analog outputs. If you'll see down here, some of these have a little tilde symbol. So 11, 10, 9, 6, 5, and 3 have this little tilde symbol showing that they can be used as a PWM output. Now we call these sort of analog outputs because we really are just generating a PWM signal. We're setting a duty cycle on that pin, and then we're assuming that it's going to be low-pass filtered, similar to how we low-pass filtered our speed sensor circuitry, in order to generate this approximate constant voltage. So if we set the duty cycle to about 12%, low-pass filtered that, we'd get approximately 0.6 volts. Again, because these are all between 0 and 5, so it's about 12% of 5. Now, duty cycles are set in the Arduino as values between 0 and 255, with 255 being always on, or a constant value of 5 volts, and 0 being a constant value of 0 volts. So, for example, up here we had if counts less than 30, gave us that 12%, and gave us this. So that's how we set these PWM signals, which give us the approximate analog outputs. We just need to filter them in order to get a real analog output. Our Arduino also has a number of analog inputs. You can see we have 6 analog inputs on the bottom of the board here. Now, an analog input will sample the voltage on that input whenever requested. So if this is our voltage applied to one of these pins, we can ask for samples at whatever time we want, and we'll read the voltage on that pin. Now this is between 0 and 5 volts again, so 5 volts is the maximum we can apply. And we're not going to get these floating point numbers out, these number with decimal places. And the Arduino internally is going to translate these into a number between 0 and 1023. So for example, if we read about 2.5, we get a number about halfway between 0 and 1032. And you can see it just translates like that for every sample. Again, analog inputs between 0 and 5 volts. Don't put anything higher on that pin or it will break. So those are all the pins that we can play with our inputs and outputs. And we can determine the function of each of those and when we read them and when we write them. There are a number of other pins on the Arduino, and so we'll quickly run over those. We have a number of power inputs and outputs. This V-in pin is where we'll supply 10 volts, and this is the supply for the Atmega chips and for the whole board. We also have 2 ground inputs, so make sure you connect those to the same ground that this 10 volts, or this V-in, is on. Now internally, remember, we have a 5 volt linear regulator and a 3 volt linear regulator. These are the outputs on these 2 pins, and so if you need 5 volts or 3.3 volts, you can pull from either of these 2, which are being generated by the linear regulators. On top of the board we have another ground, which is the same ground as all these other ones. They're all connected internally, and an analog reference input. Now we're not going to use that, so simply know that it exists and don't hook anything up to it. There's this 6-pin header on the side, which is used to program the Atmega chip in a different way, but we're not going to use it, so don't connect anything up to those pins. We also have our barrel jack connector over here, which is simply another option for connecting 10 volts. Additionally, we have our USB connector, which is how we're going to program the Atmega chip, and we're going to use a computer on your desk bench to do that. The last 2 pins we're going to look at are this TX and RX. Now previously we labeled these as just generic digital inputs and outputs, and they really are. You could use them for anything you wanted. But if you're using the serial port, these pins are tied to the serial port. And so if you're communicating with your computer using serial read or serial write, or if you're programming your Atmega, these 2 pins are going to be connected to that. So you can't independently set digital 0 and 1 and communicate to the computer. So just be aware of that. And what it really means is that we're not going to use pins 0 and 1 for very much at all, because they're already taken. So that takes care of all the hardware on our Arduino Uno. Let's take a look at what happens when we plug it into the computer. Now this second little Atmega chip that we saw up here is going to deal with all the communication to our computer. And so it's going to simply connect to our Arduino environment, and that's going to deal with talking between our main chip down here and the computer. Now when we initially plug this in, the Arduino is going to power on, and it's going to run what's known as a bootloader. A bootloader is a very small program at the beginning of memory, which runs when the chip turns on. Now as soon as the bootloader comes on, it's going to check and see if it needs to be programmed from the computer. If it does, we're going to program the chip down there. We can then power cycle the chip by hitting reset, and when it comes out of reset, again the bootloader is going to run, and it's going to grab whatever we just programmed from memory and start running that program. So really, communication and startup of our program is taken care of. The bootloader that's already on there is going to do all that for us. All we need to do is program our Atmega chip and then power cycle the board, and our program will start running as we asked it to. We're going to program the Arduino using the Arduino environment. It's going to look something like this regardless of whether you're on a Mac or on a Windows machine. This was taken on a Windows machine. Now all Arduino programs have two basic structures in them. The first one is this setup function. The second one is this loop function. Now notice functions all have what we call a return type here, which you don't really need to worry about. They have a function name, setup, and loop down here. There's then a space for input arguments, these two parentheses you can see here, and then we enclose everything inside them in brackets as you can see here. Now the Arduino is going to run the setup function once when the program comes out of reset, when it starts. So setup gets run once, anything in there happens. It's going to be usually initialization stuff. You're going to set output ports to be input and output. You're just going to initialize the system to be what you want it. You're not really going to do any work in your setup function. Once the setup function has run, the loop function begins. Now the loop function is where we're going to do all the work we need to do. We've already initialized and set everything up in our setup function. The loop function does what its name implies. It simply loops. So it's going to run through all the stuff we told it to do, and when it gets to the end, it's just going to jump back to the top and start running through again. So whatever we have in the loop statement happens in sequence over and over again forever until we turn the Arduino off. So we can take a look at a little bit more advanced program, something that actually does something. Again, you can see we have our setup function and our loop function. Additionally, above our setup function, we've defined a variable. Now, when we define a variable, we need to tell it what type of variable we have. So you can see we've defined an integer here, and then we've given that variable a name, push button. So we have an integer named push button. We've also initialized the variable by setting it to a value of 2. So we have a variable named push button, it's an integer, and it's storing a value of 2. Now in our setup function we're doing a number of things. The first one is we're calling this function serial.begin. This function takes one argument, which is the baud rate, so it's 9,600 baud. We're also setting the push button to input. Now what pin mode does is it takes the pin number, and so our pin number is 2, so we're setting pin 2 to be an input. And that's all set up. We haven't really done any work yet, we've just told it how its inputs and outputs are going to act. So once the Arduino runs this short section of code, it's going to start running our loop function. Now at the beginning of loop, you can see we've defined another variable. We've defined an integer called button state. We could have also defined this integer up here where we defined push button. Now immediately after we've defined button state, the variable, we're going to digitally read what's on the pin push button. So we're taking a look at pin 2, we're reading that value, and remember we're going to get 0 or 1 because this is a digital read, and we're storing that result in the variable button state. We're then printing that, so we're doing a print line, and what we're printing is whatever is in button state. So we're either going to print a 0 or a 1 to our serial pin. And then we're delaying, so we're waiting. This happens to be in milliseconds, so we're waiting 1 millisecond. And then we're looping back around. The loop function, remember, simply executes what's in it, jumps back to the top, and executes it again. So in this program, every 1 millisecond, we're going to read the value of push button and then print it out. Wait a little bit, loop around, and do it again. So in this program, all we're doing is we're printing the state of our push button. We're going to get a bunch of zeros or a bunch of ones on our serial port, telling us whether the button has been pushed or not. Now, we only really used integers in that last program, but there's a number of different data types that we can use. And it's important to use the correct data type corresponding to what you're trying to do. Now, the integers that we used are all just defined as int. So we've given it a data type, and then we've given it some name, and then we've initialized it. You can also not initialize right away and simply set it to a value later. Those are both valid. Now, in the Arduino language, when we define something as just an int, it's going to be assigned a number, which means it can hold either positive or negative in some certain range. And for an integer, that's minus 2 to the 15th to 2 to the 15th minus 1. This is because an integer is stored as a 16-bit number. Now, if we want to simply have a positive number and we want to maybe store larger values, we can define this as an unsigned integer. So we add a type modifier, unsigned, to our type int, and then give it a name. And the unsigned integer can store between 0 and 2 to the 16th minus 1. Now there's the same number of values, there's the same number of different values in these two, but one of them simply has half those values being negative, one of them has all those values being positive. So if you don't need negative numbers, probably use an unsigned data type. Now you can see in these names that I've chosen up here, you can really put really varied data type names. You can use underscores if you want. Numbers are fine as well, although you can't put a number as the first character of a name. You can use capitals and lowercase. Now these names are case sensitive, so valid name all in lowercase would be a different variable than just valid name as I've written it here. So be sure to check your case. That's a common error people get. They forget to capitalize something. Now if we don't need to store a data type which is so large, we can use an 8-bit data type, which is the character. Now characters can store, the signed character can store between minus 2 to the 7th and 2 to the 7th minus 1, which is about minus 128 to 127. That's their storage range. We can also have an unsigned character, which again can't have negative values, and that'll store between 0 and 255 as its maximum value. Now notice that with both integers and characters, these are all whole numbers. There's no fractional part to these. If we need to store some fractional part to a number, we have to use the floating point data type. Floating point data types can have a fractional part. You can see we've initialized this to 5.6 and this to 0.0. Now 0.0 is different than 0. 0 here is an unsigned character. We could have an integer that was 0, but 0.0 tells it that it's a floating point number. This will be important if you have to, for example, multiply a floating point number by 2. You need to multiply by 2.0, not just 2. Now, floating points can store a really large range of values, approximately minus 3.4 to the 38th to 3.4 to the 38th. And they'll have, regardless of their magnitude, somewhere between 6, maybe 7 decimal digits of precision. So these aren't infinite precision numbers. If you have two values which are extremely close to each other, they're going to look exactly the same to your microcontroller. And these are the three basic data types most commonly used. There are other data types and you can look them up online, but these will get you really pretty far if you just use these three. There are a few considerations though when using them. The most important is probably dealing with rollover. Rollover happens when we try and store something in a data type which is too large for that data type. So you can see down here in this example, we have the first character is initialized to a value of 127. Remember, if we just define it as a character, it's a signed number, so this is a signed character. Signed character has a maximum value of 127. Now we've defined a second character with a value of 1, and a third character which we haven't initialized yet. Now maybe sometime later in our program we've decided to add our first character AAA to our second character BBB and store that in our third character CCC. Now what we'd probably like is for this to equal 128. We're adding 1 to 127, we'd like to get 128. But we can't store the value of 128 in a signed character. So what's going to happen is this is going to roll over, and we're actually going to get a value of minus 128. So we're going to end up with CCC equals minus 128. See, it rolled over to the most negative value. So just be aware of how large these values are that you're trying to store in your variables, because if you're outside the range of the data type of that variable, you're going to run into some issues that you probably don't want. Now when dealing with floats, we have to be very careful. If you multiply a float by an integer, it's going to become an integer. And if you try and store something which was a float in an integer, it's going to become an integer. So as an example, let's look here. We've defined a float BBB as 5.9 and an integer AAA, which we haven't initialized yet. Now if later in the program we try and say AAA equals BBB, we probably want AAA to equal 5.9, but that's not going to happen. It's an integer. It can't store fractional parts. So what we're actually going to get is AAA equals 5. It's going to be the integer 5. When we try and do this type of conversion, it simply truncates. There's no rounding or anything intelligent about it. It just gets rid of the fractional part. So we'd end up with 5 there, which is fairly far off of what we wanted. So just be aware of that when dealing with floating points, is that they tend to get converted to integers and characters when we don't want it, and cause a lot of trouble. So just watch out for it. Alright, so let's take a look at another program. Again, we have our pre-setup type stuff where we've defined a couple variables. Here we have an LED, 9, brightness 0, fade amount 5. These are all integers, and we haven't defined unsigned, so these are all signed integers. We then have our setup function, and the only thing we're doing in our setup function is setting the pin that we've called LED to be an output type. So what we have here is we have an LED hooked up to pin 9, and we're telling it this is an output, we're going to drive a signal on that. And that's all the setup that we need. Now we start our loop function, which remember is just going to loop around. It's going to sequentially go through here. And what we first do is we analog write to the LED our brightness. Brightness is 0. We're just going to have a flat line. We're then going to increase brightness. We're going to add fade amount to brightness. So this first time through, brightness is going to now equal 5. And then we're going to use an if statement. We're going to check, is brightness 0 or is it 255? So are we at the limits of what brightness can be? If we are, then we're going to fade the other direction. And then we wait for a little bit. We wait for 30 milliseconds. Now when we loop back around to the beginning of this program, we're going to write brightness to the LED pin. And brightness is a value of 5. Remember, when we do an analog write, we get a PWM signal. So the second time around, while brightness has a value of 5, we're going to get this very, very skinny duty cycle out. And our LED is going to be dimly lit. We probably have some sort of low pass filter on that output. Loops back around, brightness gets an additional 5, so now we're at 10, and it goes and goes and goes until brightness is at a value of 255. In which case fade amount is set to negative fade amount, so now fade amount equals minus 5. And next time we loop back around, we're going to start decreasing brightness. And it's just going to bounce back and forth between 0 and 255. And we're going to get an LED which goes brighter, 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 and then reduces its brightness, and then does that forever because it's the loop function. Now if we see a program like this, we're writing one, and we see a function, for example, like delay, we may wonder why are we, how do we know it's in milliseconds? How do we know what arguments it takes? Does it have a return value? All these things. That's a good time, if you're asking these questions, to simply look it up online. The Arduino website has a large amount of reference material for all these functions. So for example, if I googled the delay function and found that, I'd get a short description, I'd see the syntax, so I'm going to write it as delay with the milliseconds on the input. It's going to give me a further description of what these parameters are, tell me its return value, and then it's going to give me a little example of how to use it. So for any function, for example these digital writes, digital reads, pin mode, all these things we've been talking about, if you're unclear about how to use them, simply look it up. There's examples, descriptions, all this stuff online, which will be very helpful for you when you're writing your program. Now when we're writing these programs, we'd like to be able to vary the program flow. We don't want to just have things go through once and then loop back around. So there's a number of different control structures that we use to do this. The first one that we'll look at is the for loop. And you can see in this program we have 3 different for loops here. A for loop takes 3 arguments. The first one is the initialization, and you can see here we've initialized it by saying this pin equals 2. Now in this case we've also declared a variable, but you don't have to. This could just be this pin equals 2. The second argument is the conditional, in this case this pin less than 8. So the for loop is going to start at the initial value, the initialization, and it's going to run while the conditional is true. So this is going to happen from this pin equals 2 and while this pin is less than 8. The last is our increment, and you can see plus plus. Plus plus simply adds 1 to it. We could have wrote this pin plus 1. And so what this is going to do is it's going to say for this pin equals 2, while this pin is less than 8, increment this pin plus 1 each loop. So what we're doing inside of that is we're setting the pin mode of whatever this pin is to an output. So this is going to say this pin equals 2, set that to output. It's then going to increment it. Then this pin is going to be 3, and so it's going to set pin 3 to output, and it's going to do that up until we get to pin 7, where it's going to set, this pin is 7, it's going to set pin 7 to an output. It's then going to increment this pin to be 8. When it comes back around, it's going to say this pin is no longer less than 8 because it's equal to 8, and we're going to stop. So this for loop right here, taking 3 lines of code, is equivalent to the 5 lines of code that it would take to individually set pins 2 through 7 to be outputs. Now we've used for loops down here as well. Again, we're starting from this pin equals 2. We're doing this for loop while this pin is less than 8, and we're incrementing this pin. So now for each pin between 2 and 7, we're going to write them high, delay a little bit, and then write them low. We're then going to exit our for loop and start the next one, where we're going to start at 7. Then we're going to do this while this pin is greater than or equal to 2, and we're going to decrement on each iteration. And so in this case, we're going 2, 3, all the way till we get to pin 7. Then in this case, we're starting at 7, decrementing until we get to 2. And then our main loop is going to jump back around and we'll start again. So for loops let us repeat things and iterate through a list of values or a set of numbers, in this case 2 to 7, in this case 7 to 2. The next structure that we're going to look at is the while loop. A while loop takes a single argument and it's a conditional. So in this case we've said while digital read of whatever pin this is equal to high, and notice how we've used the double equal sign. This is going to tell if they're the same value. It's not going to assign the value to one or the others. It's going to determine if they're equal to each other. And so while these things are equal, so while the button is high, it's going to do something. In this case, it's going to run the function calibrate. So a while loop simply loops around until its conditional is false. We have another control statement. This is the switch statement. It's fairly useful. Switch takes a single argument, in this case the range value. And then depending on the value of that, it's going to do one of its cases. So case 0 is when range is equal to 0, case 1, range equal to 1. throughout all these. So you could do this with a bunch of if statements and have if range equals 1, do something, else if range equals 2, do something. But it's a little bit more compact to use a switch statement where we can switch case 0, 1, 2, 3 right here. And so we'll do something different depending on which case we're in. Now, the way a switch statement works is it's going to say range was equal to 2. It's going to skip these first two cases because range is not equal to that. Then it's going to hit this 2, so range is equal to 2. Now, if we didn't have this break statement in, it would execute every case after that, but we don't want that to happen. So at the end of each of these cases, we have this break statement. You can look up the documentation online for this. It's a fairly useful structure which we'll use later in the labs. So once we have all of our control structures and we know how to define data types and use them, we need to figure out how do we tell our Arduino to generate these control signals, and how do we read values in from our speed sensor in order to get stuff to happen. So let's take a look at how we'd go about just piecing together this program we want to write. The first thing we have to do is decide what pins we're going to connect things to. We have our two clockwise and counterclockwise controls. We also have this on-off switch. We have our reference here. So we're going to want pin 7 and pin 8. And we're going to set those as our clockwise and our counterclockwise. And those are going to be digital outputs. We choose digital outputs because, remember, clockwise is going to either be 0 or 5 volts. So it's got two levels, 0 and 5. It's a good candidate for a digital output. Our reference output, we're going to choose an analog out, because we want this PWM signal between 0 and 5, which will then low-pass filter to get a voltage proportional. So we're going to use pin 7 for clockwise, it's going to be a digital output. Pin 8 for counterclockwise, it's going to be a digital output. And we'll use pin 9 for our reference, which is going to be an analog output. Now pin 6, you can see we have a switch over here, so pin 6 is going to be a digital input, because it's either going to be at 0 or 5 volts, and we'd like to read the value of that. And that's the first step here. We need to determine what pin we're going to connect everything to. Once we've determined that, we can simply define these. Up here you see, here's our example speed control. We've defined on is pin 6 like we saw before. And then we have 7 and 8, that's our clockwise and our counterclockwise. And 9 is our reference voltage. So we define these, and you can see here I've used the word constant, that's a modifier. And that just tells the program that these are not going to change. And they shouldn't, because these define which pin we're going to use for these. There's no reason to change that while the program's running. Then in our setup function, we need to do all of our initialization. And so what that's going to do is going to take all these pins we defined and set what type of input or output they are. So you can see we have an input for our on, as we said, and then the other three are outputs. Two of these will be digital outputs, and one will be an analog output. We've also set pin 13 to be an output. That's the onboard LED. We may or may not use it, but we've set it anywhere. And then we've initialized each of these three pins to be sitting at some known value. So we've set clockwise left low and counterclockwise left low as well. So neither of our control loops are going to be running, which is what we want when we start up. And then we've set the speed reference to be 100. So the duty cycle is whatever value that is over 255. So we have a duty cycle of a little over a third, almost a half. But it doesn't matter because both of our control loops are off because of this. This is a pretty good startup place to be. And once we're done with setup, we enter our loop. Pretty simple loop in this example. We're first going to set that LED low, so we're going to turn our LED off with the digital right. And then we have this do while control structure. A do while is pretty much just what a while loop is, except instead of checking the conditional at the beginning of the loop like a while does, it checks it at the end. So a do while will always execute once. In this case it doesn't matter, we could have used a while loop because we're actually not doing anything. But what we are doing is we're saying digital read pin on equals low. So while our on-off pin is low, so while we're off, simply loop in this loop, and we're going to loop here forever until pin on is not equal to low, in which case we'll hop out of it. So what this does is this pauses program execution pretty much until we've turned things on with that switch. Once that happens, we do another digital write on our LED, and we set it to high. We then wait for 1000 milliseconds, so we wait 1 second, and then we're going to set our clockwise control output to high, so that's going to start up our control circuit on the clockwise direction for that wheel. We've already set a reference voltage up here. Remember, we did our analog write. So as soon as we set this, our robot's left wheel is going to start turning clockwise at a duty cycle of, or at a speed of 100 over 255. So at about a third of full speed, it's going to start going clockwise. We're then going to wait for another 3 seconds, and then turn off that clockwise control loop and stop our robot. Now what that's done is we've waited while we're stopped, we've then spun for 3 seconds, and then we've stopped. Now we're going to loop around because our loop just loops forever. I'm going to get back to the top, turn off the LED, check if we are still enabled, check if our switch is still on. If it is, we simply skip this. Then we're going to turn our LED back on. We're going to wait for a second, and then we're going to turn our wheel back on. So you'll notice that if pin on is high, and so this never gets executed, pretty much we're just looping these last 4 lines. We're toggling an LED as well, but that's taking pretty much no time. So what we're really doing is we're waiting a second while the robot's off, turning the wheel on for 3 seconds, then turning it back off, waiting a second, so we're spinning for 3 seconds, stopping for 1 second. And then with this program, you'll notice that for these 4 pins, we've defined them as a constant, 6, 7, 8, 9. We could have done the same thing for this 13 we're using all over. We've just used 13 because we know that's where the LED is, but we could have defined another constant integer, named it LED, and said that's equal to 13, and then we could have had pin mode LED is output. It would have made things a little bit clearer, and it's probably a better way to have programmed this. But in any case, this program will, when run, cause our robot to spin in circles for 3 seconds and then stop for a second, and we can enable and disable that with a switch. So that's the basics of how to get this Arduino to work. And once we have that in place, you can imagine we can change what's in that loop to change exactly what the robot's doing. But that's enough to get started with Lab 4, and should really carry you past the first half of the lab.